cis and trans naming. In chapter 7, you're going to see that kind of translates into something we call E and Z. And so just going along the double bond, we're looking at the groups, right? So at this carbon, what's the bigger group? This methoxy, this ethyl group. And in this carbon, here it's just an implied hydrogen. So at this carbon, this one is the bigger group. So along this double bond, both groups are on the same side. And so that is called Z. Z, same side. Opposite sides is E, which here we have an example of that. So along the double bonds, at this carbon, we see that here is our bigger group. And at this carbon, this is our bigger group. So E is opposite sides. Christy's asking, Z basically cis. Yeah, so E and Z can most often be used interchangeably with E and Z. There's only like one exception. I'm sure Chris will go over it in SI, but E and Z is referring to like priority groups, and cis and trans is referring to like whether or not there's the same groups or different groups. So if the there's very few molecules that you come across. This is an example of one. I'll draw one here. Let's say bromine, and iodine. So this is an example of like one of the only times that you'll see that E and Z won't be interchangeable with cis and trans. Other than that, cis and trans can easily be interchangeable with E and Z and vice versa. So on this next exam, you're going to see less and less of cis and trans and more E and Z. So if we were to name this, molecule here, of course, going back to our IUPAC rules, we want our substituents and our groups on the least numbered carbon possible. So let's say, let's do this. 1, 2, 3, 4, 5, 6. So that's here we have a hexene because of this double bond, the suffix changed to an ene. And we have this methoxy on the third carbon, and our double bond is on the third carbon as well. So in conclusion, for that example, you're often going to see it in parentheses. So first and foremost, you want to designate whether or not it's E or Z. So for this example, we determined that it's already Z, so Z in parentheses. And so you're just going through your IUPAC. So so you have methoxy on your third, so 3 methoxy. then you go to your parent chain, because that's really it, hex. And your double bond is on your third carbon, so hex 3 ene. And similarly with this one, we want our substituents on the lowest number possible. So let's do this 1, 2, 3, 4. And this is a phenyl, not a benzyl. This is a phenyl group. Here we have a methyl and an alcohol. So we already determined that this is E, because along this double bond we see that the biggest groups on the opposite carbons are on the opposite side. So the name of this carbon would be parentheses E, E, okay, E. E, our phenyl is on our fourth carbon. So for phenyl. And we have a methyl on the, we have a, actually, no, this is a 5, my mistake, 5 carbon ring, 5 carbon chain. So we have a pentene. So for phenyl, pent, the double bond is on the third, so pent 3 ene, but you have your alcohol in the first, so 1 all. And again, this, I don't know why it's drawing it like that, but this E. Okay. So these are the names, IUPAC names for these. These are 2 examples that I've seen. All the examples that I'm showing you today, other than 1 or 2, I've seen on bonding assignments. Next, we are looking, I don't know if you went over it in the video lecture, but maybe he did. This is kind of a fundamental thing. What undergoes dehydration the fastest? And what you're going to look for is the classification of the alcohol, whether it's primary, secondary, tertiary. And so does anybody know if what will occur the fastest, primary, secondary, tertiary? That's right, it is tertiary. So the trend will be tertiary, secondary, primary. But here we see that there are 2 tertiaries. So the idea behind the tertiary is that when the leaving group leaves, right? When the leaving group leaves, a carbocation forms, right? But the carbocation wants to be as stable as possible, and tertiary is how it will get that. Tertiary carbons are more stable than the latter. So primary, that's out. This is secondary, that's out. Here we have tertiary and another tertiary, and so the only exception, the thing that will go beyond faster than a simple tertiary is tertiary with resonance. Okay. This benzene is able to resonate around itself, and if there's any electrons over here, it will donate and withdraw within from that ring. And so this will undergo the dehydration fastest compared to this tertiary. Does that make sense? Okay. So you may be given a question just like this, but given only the names. So you're going to have to draw it out, because obviously we can't, unless you're unless you just go through the 5 to 10 minutes of mental gymnastics, you're not going to know what's primary, secondary, tertiary. So A will look something like this. We can already see that this is a secondary substrate. This is B. We see that this is a tertiary substrate, so this is obviously better than this one, so this one we can cancel out. So this is B. C will look like this. What is this? This is primary, so that's very much non-ideal. This one will look like this. This is primary as well. So we see that B is the answer. It is the tertiary and most preferred dehydration substrate. Moving along to some reactions. So as far as I know, he went into elimination reaction. And so one thing, I don't know how far you guys got in SI though, but if you haven't gotten to it yet, take a picture of this. Take a picture of it, know it, love it, because it will be what makes you pass the third exam. If you have the substrate and leaving group. If the leaving group is primary, secondary, tertiary, then you look at what reactant, what's reacting with it, the nucleophile base. If it's strong, strong, weak, weak, strong, weak, weak, you'll be able to look at this table, piece it all together, and figure out what type of reaction is occurring. And so this reaction throws together substitution and elimination. So get to know this, you're going to need it. So to walk through that example here, we have a secondary leaving group, okay? And we have sodium ethoxide. Again, going back to our acids and bases, the sodium is just going to dissolve away until we have ethoxide. What's that look like? This here is ethoxide. Obviously it's not working. So this here is ethoxide. It is a strong, strong nucleophile base. So secondary, strong, strong. So I'm going to go and undergo an E2 mechanism. That's how you use this table. We'll undergo an E2. So it's all going to happen in one step, kind of like SN2. E2 is going to happen all in one step. But you have one other thing to look at, and it is this, your Hoffman Zaitsev rule. Your Zaitsev rule states that if you have a bigger base, well, if you have a small base, the base will attack a hydrogen that is in a more substituted position. Okay, so that makes sense, right? If you have something that is smaller, you're able to fit it into something that is more crowded. Okay, so looking, for example, this carbon here is more substituted than this carbon here, right? This carbon is attached to two other carbons. This carbon is attached to one. So this is the more substituted, this is less substituted. So if we have a smaller base, it's able to fit into something that's more crowded. And that is why if you have a smaller base, it will react more readily with the more substituted position. So here, with leaves, you have your alpha, your two betas. Here, you have hydrogen on both. This carbon is attached to one other. This carbon is attached to two others. So this carbon is the more substituted, and the sodium ethoxide will take a hydrogen from there and we'll create a double bond between the alpha and the carbon that it took from. So the major product will look like that with sodium methoxide. Tert butoxide. Tert butyls are the only big base and nucleophile that you're going to encounter in this class. So again, tert butyl looks like this. This is your functional group. This is the only big base. So whenever you see tert butoxide or tert butyl, it's going to go with the Hoffman, which means that it is simply the opposite. It will go towards the less substituted side because, again, it should be conceptual that if you have a bigger something, it can't fit into something that's more crowded. Right? So if you have tert butoxide, it'll go to one of these hydrogens because it's less substituted, it's less crowded. And so if you have tert butoxide with this, the major product would be that. Does that make sense to everybody? Similarly, with this example, can we do that again? Yeah, I'm going to go ahead with this example here. So Br is going to leave. So you have, again, this is an E2 mechanism, but I'm just going to break it down. So this is your alpha carbon. Your alpha carbon is wherever there's a charge. Again, to walk through the mechanism, I know that it is a E2 mechanism because you have a secondary leaving group. And you have a strong nucleophile base. I know this because the table. Again, this table will make or break this next exam. So again, look at the leaving group, classify it, look at what nucleophile there is, classify it, and piece it together. So we know that this is a secondary leaving group. We are using sodium methoxide, which is here. And so we know that it is strong, secondary, E2. Simple as that. So, going back. This is more substituted. That carbon is more substituted because it's attached to 1, 2, 3 carbons. This position here, this carbon is only attached to 2 others, 1, 2. So this is more crowded, right? So this has a implied hydrogen. This has the 2 others. So you have a small base, and its small bases are able to go to places that are more crowded. And the Zaitsev rule. The smaller bases, like sodium methoxide, are able to squeeze in and take a hydrogen from the more substituted beta. So you're going to see that the sodium methoxide come in, take that hydrogen, and form a double bond here. Contrarily, if you have tert butoxide, it's the same mechanism, but it's just a bigger base. Bigger bases will have to go to the less substituted side, and so that's this one here. So the tert butyl will take hydrogen here and form a double bond between that beta and the alpha. Does that make sense, Chrissy? All right, so and another thing that he may or may not throw out there is if you see examples like this, these are not going to react. And so the reason all comes down to axial and equatorial. You can read the book if you want, but if the leaving group, I'm going to write it also. if the leaving group and a tert butyl are axial, then there's no reaction. All right, so again, remember from chapter 4, our axial and equatorial position, they're kind of opposites. So one will be axial, the next one will be equatorial, and back and forth, back and forth. So we can ambiguously say that this is, just say that this is an axial position. So axial, equatorial, axial. These both, the leaving group and tert butyl are in the axial position. And so therefore, you're not going to react. So just take a picture, take note of this. These two are examples of something that will not undergo a reaction. Next. Again, the major product. Again, the major is the most preferred, the most stable, and most readily produced. So again, this is just like the others. OTS, you don't have to know what it is. You're going to encounter it a lot in Orgo 2. OTS is a really good leaving group, so it's going to leave. This is sodium methoxide. Again, we have a secondary, and we have a strong, and so we have a E2 mechanism. But to break it down for you guys, here's our alpha carbon. So this is the more substituted side. This is the less substituted side. So where is the sodium methoxide going to go? The more or less substituted side? More substituted because it's smaller. It's able to go to the places that are more crowded. So your double bond is going to form here. When you do these problems, can yep. Can you guys still see the table? So as you can tell from the table, the elimination reactions are more so going to occur in secondary and primary. You're not really going to have to worry about it with primary. Its elimination reactions are more so going to occur in secondary, tertiary. That's why you see a lot of these examples with secondary leaving groups. But here we don't have a sodium methoxide. We have a tert. So this formula here is just saying that there's 3 methyls. So the leaving group is going to leave. Again, it's an E2 mechanism. If you go to the chart, it's in, I believe so. Yes, it's an E2 mechanism. So it's all going to happen in one step, but I'm going to break it down to show you guys the carbons. So we have, there's our alpha. We have 2, again, we have our typical 2 options for beta positions. We have beta, beta. Again, there's no difference between the 2. So don't overthink it. Your double bond will form between the alpha and the beta, just like that. And here again, the tert butyl, we have a tert butyl, it's going to go to the more substituted side. And so therefore, well, actually, I said that wrong. The tert butyl, because it's a big base, it will go to the less substituted side. So that's going to leave. This is the less substituted compared to this. So this tert butyl, go ahead and take a hydrogen from there, and it will look All right, so, okay, this the time is almost up, so I'm just going to go right to this. It's possible for, okay, like SN1, you form an intermediate, right? So E1 will also do the same. E1 mechanisms will form an intermediate carbocation, which we've been talking about this whole time. And if, again, like we've seen before, tertiary will always be preferred than the latter. So tertiary is best, primary methyl is the worst. And so if the molecule can go from a less stable to more stable carbocation, it will. And it will only do that via something called methyl shifts and hydride shifts. And those only occur in E1 mechanisms because there's that carbocation intermediate. It does not occur in E2. So if you go to this table, you'll see that this is a E1 mechanism. And so it's going to form an intermediate, which will look like this. This, again, going back to our chapter 4, this is a non-ideal angle. There's a lot of ring strain going on here because this is a 90-degree angle. We would prefer a higher degree. So it's going to, so this bond is going to break and a new bond is going to form. And that will expand the ring. And it will look like this. Something that I have always liked to do is I like to number my carbons. So 1, 2, 3, 4, 5, 6. And you'll see after doing this, 1, 2, 3, 4, okay? You'll see that 1, 2, 3, 4. So here you expanded the ring, but the carbocation is still in a secondary position. You have a hydrogen here that is able to do a hydride shift. So that hydrogen will move, and therefore the carbocation will go to where the hydrogen came from. And your new alpha carbon is here. Now we have a preferred substrate that will readily undergo an elimination reaction. So this is a tertiary substrate. That's why it's preferred. So we also have a big base because of the terbutyl. The bigger base will go to the less substituted side because of its size. So you'll see that this carbon here is less substituted than these ones, right? Because this carbon is only attached to one. These carbons are attached to 2 others. So it will take hydrogen from here and form a double bond between that carbon and the alpha, and your final product will look like that. He's not, again, this is as complicated as he's going to make it. So if anything, you can take an L on ring expansions. He shouldn't do any more than 1 or 2 problems on the ABM. So that is all I have for you guys today, because time is up, unfortunately. So I'm going to go ahead and stop sharing. But I'm going to stay back for a few minutes if you have any other specific questions.